Jai Hind all. Myself Amita Asthana from Ajay Kumar Garg Engineering College, Ghaziabad. In this video lecture, we will study about the subject Digital System Design. The subject code being KC 302 for digital systems, and the topic would be 4-bit parallel adder subtractor, and one more topic we will discuss, that is Bcd Adder. Right. So 4-bit parallel subtractor we are going to discuss. So here, if I have two numbers, this is A, this is A, and this is B. Okay. 4-bit, that means the number A will be having 4 bits and B number will be having 4 bits. So here this is my A0, A1, A2 and A3. Similarly here this is my B0, B1, B2 and last one would be B3. While I am subtracting from A to B, the operation is A minus B. So A0 minus B0. Starting, there is no borrow. Borrow initial is equal to 0. So now I will put all these values. The halves, this is full subtractor, or we can take it as half subtractor because there is no carry input. There is C initial. Since this C initial is equal to 0, so we can take it as a full subtractor or half subtractor. Both ways we can perform. So here this A0. Coming to this A0. A0 is equal to 0. All the values we will write here, 0, 1, 1, okay, and B0 is 1, 0, 1, 0, okay. If it is a full subtractor, then I will write here 0, otherwise we can leave it. So the answer, that means D0, the difference D, D0, D1, D2 and D3. We are getting from the output of each full subtractor, and these subtractors are connected serially. So we can say that these are inputs are parallel, but borrow wise they are connected in a serial manner. So final borrow will be given from here, that means borrow. Now full subtractor circuit we have already discussed, that how the full subtractor circuit works. So in a similar way, the output would be here, the output would be 1, 1, 1 and 0. How this is coming? So initial is 0, or you can say that is nothing. So 1 and 0 XOR. We know that in the subtractor circuit, the subtraction, the difference comes out by XORing the inputs. So here 1 and 0 XOR would be 1. Similarly here, the XOR of the 3 will be taking place. Similarly here, the XOR of these 3 bits will be performed like full subtractor circuit, and borrow from the first stage, borrow from the second stage and borrow from the third stage. Okay. So this is borrow. borrow, these are all borrow. The borrow bit and A1 B1 XOR will give the D1. The borrow 2 bit A2 B2 XOR will give the D2, and similarly here. And this is the complete full subtractor circuit we are taking, and hence we can design a 4-bit parallel subtractor circuit. Similarly, the subtractor circuit, if you replace this by a full adder, then we can get the full 4-bit full adder circuit also. So, subtractor and adder circuit for 4 bits are easy, but the module will be the same as we have already discussed in previous videos. Now, one more operation we can perform, that means we are going to discuss a circuit in which we can perform both the operations, that means addition and subtraction simultaneously. So, the concept is this XOR gate. First is this XOR gate, right? And second one is this M bit. Okay. So, let us see how the circuit is working. This is complete full adder circuit. This is also a full adder circuit. These all are full adder circuit which are being cascaded by the carry from the previous stages. Now here this is the S0, S1, S2, S3. When the addition will be performed, this will give the addition answer, and when the subtraction will be performed, we will get the difference bits from the output, and final carry or borrow output will be obtained from this point, right? Now coming to the two main component of this adder and subtractor circuit, that is XOR plus M bit. So when this M is 0, let us see what happens. Set M is equal to 0. Okay. Set M is equal to 0. Now, this 0 will be transferred here. 0 will be here. 0 will be here. And 0 will be here. Right. When this M is 0, so whenever the M is 0, let us see what is the output here. Okay. So, for XOR of any number, if XOR, let's say B0, if B0 is 0, the answer, the output will be 0, and if B0 is 1, the output will be 1. Okay. So, whenever M is 0, the output is B0 here, and here it is B1, and here it is B2, and here it is B3. Okay. So, these are the outputs of the XOR gate, and the circuit will work as adder circuit, right? For M is equal to 0, the circuit will work as adder. Now, next case, when M is equal to 0, M is equal to 1, let us see what happens. Case 2, when M is equal to 1. So, whenever M is 1, let us see what comes here. This is B0 and this is M. M is 1, B0 may be 0, so output will be 1, okay. And if B0 is 1 and M is 1, because in this case M is 1, so the output is what? 0. That means whenever I am fixing this M at 1, the output is B not bar. Okay. So, this is B0 bar, this will be B1 bar, this will be B2 bar obviously, and this is B3 bar, okay, and here it is 1, 1, 1 and 1. Similarly here also, because if m is equal to 1, then it is same as we are adding the 2's complement of B0. So taking the 2's complement and adding to A0 is same as we are doing the subtraction part. So whenever the m is equal to 1, it will be working as a subtractor. So these two parameters are important. First is the m and the XOR. So for binary adder and subtractor, the circuit will be same as the serial adder and serial subtractor 4-bit, and only by addition of one additional bit, that is m, and XOR and 4 XOR gate, these two will combine and the circuit will behave same as adder, as well as it can behave as subtractor also. Now coming to the next topic, that is BCD adder. Now we are very well aware for the BCD codes from 0 to 9. From 0 to 9, we are having the BCD codes at same binary numbers, especially the BCD codes are given by 4 bits, that all we know, it is given by 4 bits, and in the BCD code we are having these 6 forbidden codes, and these 6 forbidden codes are starting from 10 to 15, right? So 10, 11, 12, 13, 14, 15 are not defined for the BCD code, but because the pattern is the BCD is written in the A8421 weighted code, so here we can say that only 10 codes are authentic, and otherwise these all are illegal codes or forbidden codes. So that was an introduction for the BCD code. Now coming to the BCD adder. So for designing the BCD adder, what we can do, that this is the input in the BCD form, this is also the input in the BCD form. The concept is whenever on addition we are having 0 to 9, A may be from 0 to 9, B may be from 0 to 9. Okay. So if the sum of A and B exceeds 9, okay, exceeds 9, sum is greater than 9, then it will give obviously the forbidden codes. So we have so many combinations where we are getting the sum of A and B to exceed from 9. So what we do is, whenever we are having the illegal code, we perform an operation, that is error correction, and that error correction is done by adding 60110 to the sum. Okay. So whenever the sum is less than 9, the regular binary addition will take place, and whenever the sum is greater than 9, we need to apply a corrective procedure of adding plus 6 to the sum, right? Now here is the table we can make. So when the 0 to 9 sum is coming, it's okay, it's all okay. We can design the circuit as 4-bit parallel adder, right? But if the sum is exceeding 9, then let the sum is 10, 11, 12, 13, 14, 15. Here the possibility is the sum for two numbers, like if A is 9 and B is 9. So sum may be, there are cases where sum may occur from 10 to 18, right? For 10 to 18 cases, we need to apply a corrective action. Otherwise, we have a regular binary addition. So in this, the sum is, if the sum is 10, the answer will be 0, 1, 0, 1, 0. If the sum is 11, that will be 0, 1, 0, 1, 1. And in the similar way, we will write all the combinations. Similarly, sum may be 16 and 17 and maybe 18. So the cases are 1 for 16, that will be 1, 0, 0, 0, 0. And for 17, that will be 1, 0, 0, 0, 1. And for 18, it will be 1, 0, 0, 1, 0. So this is the maximum possibility we are getting. Now the corrective action. For corrective action, what would be the carry in all the cases whenever we are adding? So here, let's say we are adding a 6 to this. So this is the K. Let us consider P0, P1, P2, P3 is the answer which is coming out whenever the sum is greater than 9. By applying the corrective action, we can have a C out also, and that is the sum Z0, Z1, Z2, Z3. Okay. So what needs to be done here? For applying the corrective action, this case is okay. The sum is between 10 to 19. We can apply a correction. From 16 to 19, case 1, from 16 to 19, K is set to 1 and we need to add a binary quantity, that is 0, 1, 1, 0 to P3, P2, P1, P0. Here we are going, these all are the cases where corrective action is needed, right? And in this we have already distributed in the two cases where this K is 0 and whenever this K is 1. So coming to the next slide. And another one, whenever that sum is 10 to 15. So K, P3, P2, P1 are set to 0, 1, 1, 0, 0. Here is the series for 0, 1, 1, 0 and need to add 6 from 0, 1, 0, 1, 0 to 0, 1, 1, 1. So here we can say from 0, 1, 0, 1, 0 to 0, 1, 1, 1, 1 from 10 to 15, right? So case 1, 16 to 19, K is set to 1. Apply the corrective action. Okay, 10 to 15, the case is K, P3, P2, P1, P0 are set to 0, this one. Need to add 6 again. Now, we can apply the K-map procedure for solving this truth table. So, the truth table has been made and we need to apply the corrective action and we will solve the K-map for the C out. Okay. So, the C out case, we will solve the K-map, and for the designing of BCD adder, we can solve from K-map, that will come out to be C is equal to K plus Z8 Z4 plus Z8 Z2. So, the addition of binary 6 to the binary sum converts to the correct BCD code. So, output carry is also required to be represented and we can apply the K-map for getting the carry. So, here we can consider that the carry is 1, for which cases the logic can be applied. The carry is 1 for which cases? Whenever K is 1 or Z8 Z4 is multiplication is 1 or Z8 Z2 multiplication is 1. So, for all these three cases, we are having the C carry out to be 1. So, here The decimal parallel adder we can apply for 4 bits, and here n is equal to 4, and the circuit can be designed as follows. We will need two 4-bit parallel adders here. The ICs are 7483, two ICs we have taken. So A0, B, these are the two inputs, the B number and the A number. The sum will be given here, and whenever this C is equal to 0, see, when everything is depending on this particular output. Why? Because if it is 0, let's say, if it is 0, okay, if it is 0, then this output will be given by S0 into S1. See here, this S0 plus S1, the OR, and then multiplication. This is the corrective logic. This is the corrective logic we have designed, that this is S3. Okay, S3 into S0 plus S1 plus this S4. Same is we have derived. See, K plus Z8, Z4. Z8 means S3, Z4 means S2, and S2, S1, S3, and this is carry out. This one is for K. K means this S4. This is K. S3, S0, S3, S1. So here if whenever this output carry X is equal to 0, see, X is equal to 0, no addition will take place, no correction will be given. But whenever this X is equal to 1, the corrective action will take place, and we can have the sum from these two, and this is not used, or this carry is being discarded, and hence we can design the BCD adder circuit. Thank you.